Good afternoon, everyone. Let's continue our course first, then share screen. Okay. We will gonna to continue to load the data from the climate models without downloading. Let us rerun the previous code. Let's read the Excel. And we filter the data to what model that I want. And we have a loop of the models. Yeah. And in morning, I already introduced you the function that we will use to change the time actions of all the models. Then we will use this function and loading the data from the Google Store. Okay, I think we can continue from here. Yeah, in general, what we will do is to use the link from the store. You can see from the Excel. So these links, we only need these links because these are the links that where the data was stored. We will get these store links, and then we define a dictionary. The dictionary is a data format in Python, and it looks like we can select the data inside the dictionary by using the key. So this name is the key. So first, we create an empty dictionary named ensemble. It represents the multi-model ensemble from the GCM. Then, because I made it in this style, is that in some cases, we are not only dealing with one variable. For example, in our case, we only deal with the surface wind speed, but in some other case, we may also deal with maybe the variable like temperature or precipitation. Every time when we create an empty dictionary, we can create another dictionary within it by using a key. For example, here I create another empty one by using the key wind speed. And then the same, we can continue to create an empty one by add a key using the experiment ID. Therefore, this will be an empty dictionary for surface wind speed under SSP 8.5 scenario. For sure, if you change the key here, you can create other dictionary, and you will store all the models, all the variables, and all the experiments in this dictionary, in this main dictionary. It's called ensemble. And for sure, so here we will create a loop to get every context in the link. For example, we get the model ID, variable ID, and the experiment ID. Then we will call a function to visit the link. Okay. Once we visit that link, we can use this OpenZara. It's from the XArray package, because this kind of cloud-based XArray is has a format. It's called Zara. And we already import the Zara package so we can deal with this type of data. So we read every single model into the DS. And then we given some logic to transfer the latitude into lat, longitude into long, because in some dataset or in some models, the name of the latitude is latitude, but in some the other models, the name is lat. So we write this to ensure the variable name, also the name of the special location is the same, it's the constant. And we did the same as in previous step. We select only the time span from 2050 to 2100. And then we will call the function. This is the function name we defined in the previous cell. So after we read the dataset, we call this function to transfer the time axis into what we defined, into the format we defined. So after this process, the dataset will be has the same special name and also has the same format of the time axis and the same time span. So it will be much more easier for our later analyze. And we, like here, we do some check if in the dataset we can find the name called wind speed, or if we can find the latitude, longitude, and time axis. Otherwise, the dataset is not correct. Okay, so this is to make sure that we get the right dataset. And finally, we put the loaded data into our created dictionary, and we give a new key. The key is the name of each climate model. So now we can, after we load all the climate models, we can easily visit the data for a specifically model under experiment and for the wind speed. So in this structure, it will be very clear which data are you using. This example, which model, which experiment, and from which model. And then, like for every time we print this information to make sure that we successfully load the data from one single model. And this is like if we, for example, in some models, their time access is very complex to deal with. So here I just use this logic to skip it because I'm just going to give you an overview of how to load and analyze. We are not going deeper into like how we deal with every different time access format. Okay. So if we face some problem for some models, in this case study, we just skip it and we only keep the model is format as our defined function. Okay. So we can try to run this step to see. And because I already run it before, it took around 2 minutes and 30 seconds for loading the 22 models. So let's wait here. And I forgot, after we load each models, in the end, we can print a summary. So print a summary, like here, we loaded how many models and we skip how many models. So it's a summary of how many models we have succeed in loading into our working environment. And here you can see while the cell is running, every time it finish the loop here, and it will print the model name in this loop. For example, here, the GFDL, SSP, and surface wind. So it means that this loop is finished. So loop. Here you can see all the models, the name is exactly the same as the name here, because we get the link from our filtered data frame, not the entire one. If we load the entire one, I think it will take, I don't know, maybe around 20 days. Or the Colab cannot support you to load such a big data set. Okay, here you can see, for this model, we face an error. This was catched by our error catcher here, because in this model, you can notice that it also shows the detailed information about this error. You can see the invalid data number provided in the CFT time. So it's cased by, in this model, they use this type of time format. It's called CFT times date time, 360 days. It means that in this model, each year, it only has 360 days. So it cannot be directly transferred by using our defined function. It may need some specific treatment to transfer this time access. But as I mentioned, we are not going to be in such detail. It's enough for us to just load the easier one. So now you can see, yeah, we already load the 22 models and we skipped one of this one, okay? So now we can have a quick look. For example, every time if you are not clear what is inside our data or in the variable, we can print it. So we can just write the example. It's the name of the dictionary here. We run it. So it will give a very detailed information of what is inside. You can see here a lot, because we have 3 layers. The first layer is the variable key. We have the key of the wind speed. And then is the second layer is the experiment. Actually, in our case, because we only use one variable and one experiment, we can make it more easier like this. So it's actually, we can have a look at this dictionary. Here we are. You can see in this dictionary, it contains 22 models wind speed data on the SSP 8.5. And if you want to visit a specific one, we can easily visit by using the name of the model as the key. For example, here we add the name of this model, and then we run this cell again. Okay, you will get the exactly data set of that climate model. You can see the time span is from 2050 to 2100. And for each month, we only have one value, because in our function, we already select a maximum daily wind speed of that month, okay? And then, so this is the variable surface wind speed, and you can see here the latitude and the longitude. The latitude is 180, the longitude is 200, 288. It's a global one. So it's the original global resolution of these climate models. Because in the previous step, we only deal with the time axis, okay? And as I mentioned, you can see for different models, their spatial resolution is different. For example, here, I'm not gonna just select a specific one. You can see their information here also. Like in some models, the latitude grid only have 94 and the longitude is 192. So it's totally different with the previous model, with this one, okay? So the larger the number, it means that the spatial resolution, the model is. Here, we can say the spatial resolution of this TIE ESM is better than this IITM ESM because it's actually the latitude is 2 times than this IIT ESM, and the longitude grid is 1.5 times than this IITM ESM. But you will find that for not every model share the same spatial resolution. It will make us to face some problem when when doing some spatial analysis, because for each model, their grid, the size of their grid is different. So the location of their data point is different, and it's very hard to make some analysis. For example, we want to calculate a mean value from all the models. If we use the raw output directly, it will raise a problem. It will raise an error because in general, the XLE package or some other packages, they can only deal with the dataset with the same spatial resolution. Okay, so next step, it's a very important step, is that we need to regrid. What it means regrid? We will change the grid resolution for every model into a common 1 degree plus 1 degree target grid. And this 1 degree and 1 degree can be defined by your aims. Here I select 1 degree plus 1 degree because it's not that close and it's also not that accurate, not that fine resolution. So it will reduce the time for our calculation. For sure, the finer the resolution, it will take longer time to calculate. You can also change it to 0.25. It's the same spatial resolution as the error file. But in that case, in that 25 kilometer case, it will make every model, the data of every model very large, and it takes a very long time to analyze. And it will also cause some problem when you calculate it, because it will ask more computing resources and in general. And another important influence is that the data format here, you can notice it's not exactly the number, because let me show you. By this way, without download, we are not loading, like even until this step, we are not loading the data into this memory. You can see it's not the exactly number of that variable. It's a data type. It's called task array. It's type of the data which is used for the parallel computing. And the data is still in the cloud. Only when we are calling to compute it or plug the result, it will be computed into our working environment. Okay. So even until now, it's not inside our environment. So the exactly number is not inside our environment. You can consider it's like a link to that data set. And in this format, it will modify. For example, it will have a chunk size. So it's changed you can imagine it has each time step is a figure for the whole data set. So it makes it as a chunk. So every time when you are computing it, it will compute chunk by chunk. So you can see it's reduced the entire size of the data set into the small chunks. And it will make the computation more efficient and cost less time. Then here, our target. So first, we will create a target grid. So here we will create the target grid from negative 90 to 90 degree above the latitude. Okay, and in each step, we give it 1 degree. So it will be 180 degree in the latitude. And then in the longitude, we do the same. Let's start from minus 180 to 180. And also use the same special step for the 1 degree. And therefore, we will have a grid size of 360 degrees in the longitude point. Okay, that's finally the depth target. It's the target grid, the target 1 plus 1 grid we want. Okay. And then we select the latitude and the longitude from the target. It's from our defined target. And here is a function that is to help us to transfer the longitude into 180, because in some climate models, their raw latitude start from 0. They start from 0 and then ending 360. So we need to transfer to this formal negative 180 grid. And also we need to ensure the latitude and the longitude are sorted. So it's exceeding. And because only is the latitude and longitude under this kind of format, it can be done by the auxiliary to interpolate into the target data grid. And finally here, we define a function to do the exactly regrid by using the bilinear regrid. So here, as I mentioned, we first ensure the latitude and longitude is sorted, and we transfer all of them to the minus 180 grid. And then we choose the variable, and we make it into the time, latitude and longitude, because that's why it's complex, because as you can see here also, in some models, not this one. For example, in this model, the variable is indexed by time, latitude, and longitude. But in some others, this might be different. Okay. Oh, this one. Okay, so here the dimension. You can see the dimension in this GCM. The dimension is time, latitude, and longitude. In this one is latitude, longitude, and time. So every time we also need to ensure the sort of this name of the variable index is the same. So we transform it to time, latitude, and longitude. Finally, we can use the target latitude and the target longitude by our definition and use the method bilinear interpolation. So we will get a dataset which is regraded dataset has a 1+1 degree. Okay. So it's 100 kilometers plus 100 kilometers. And finally, this function will return this data set after the regrade. So we will do the same. We create a new empty dictionary called ensemble 1 degree. So now it's a dictionary for all the climate models after our regrade process. So all the climate models within this dictionary will have the same spatial resolution of 1 degree plus 1 degree. And here, this one is useful to skip some if they face some error. Okay, because in our case, all of this has success because we already made them has the same format. And then it's the loop or loop into the original one. Here you can see we looped by using the key. So what is this key? This key is all the name of the climate models. Okay, you can have a look of this one. We can have a look here. Okay, you can see we can get a list from all the keys within this dictionary. And then we use the loop. For each time, it will select one name of the climate models. And then we select this dataset and we call the function. We call this function. And it will give us a new dataset has a resolution of 1 degree plus 1 degree. And then we put this 1 degree dataset into this new dictionary. And then we print, oh, okay, for this model, we finished. And within this loop, it will do the same process for every single model. And finally, we will get this dictionary for all the models. And as the same as we dealing with the time axis, we can give a summary in the end. Like after all the regrade, we can print how many models are we succeeding in regrade into our target and how many are skipped. Okay, we can do the same. So we can click the rounding cell here. And it will have the same, like you can see, it's very quick because for this, even after the regrade, we are not loading the data inside our memory. Actually, in this step, it's kind of like give a logic to the Zara dataset. So after in the later process, every time when we use the example 1 degree, it will first interpolate and then make the calculation. So it's not calculated here. It will calculate later. But you can see here, the spatial location, the spatial coordinates has already changed. Okay. And you can see actually the size of each data set has increased because we increase the spatial resolution. In some cases, their longitude grid is lower than our case. So that's, you can imagine, if you want to create a latitude and longitude with a grid 25 kilometers plus 25 kilometers, it will be larger than gigabytes, okay? So it will be very large, very big. And so for that case, I don't recommend to regrid the original raw output for global one into that final scale. Only if you need it, only if you need to do a very fine resolution analysis at the global scale. But in that case, you cannot deal with all the models all together at one time because it will ask a lot of computing resources. I recommend to deal with every model at each time. Okay, after we get the regrid dataset, as I mentioned here, it's still not into our memory. And we can have a quick look of the surface speed in the Strait Messina at 2099 from the 22 loaded models. Only in this step, only when we want to plot, only when we computing the real data, the real number of the wind speed will be loaded into our memory. So first, we define a region. The region here is the same as in our previous notebook. The region bounds for the Strait Messina. And then we will compute the annual maximum daily wind speed for one model. We define this function just for one model. And so we select the variable wind speed. We use the year from 2099. For sure, you can change the year here, okay? And the logic is very similar, it's the same. We read the data and we select the time span and we make sure the data set is correct and we crop because our previous one is global data set. So we only select the range within our target, range within the Strait Messina, okay? And then it will return this area. So it will give us an area data set. Okay, and we select all the dictionaries and we create this list to store our result. We store the regional result. And we store the names that it succeed, okay? And we do the same, we use the loop. And for each loop, for each model, we call the function to calculate the annual maximum wind speed. And then we put it into this list, okay? So in this list, it will list the 22 results for 22 models. And this will keep all the names of the succeeding models. And if there is an error for some model, it will skip, okay? If not, so we've got many models. And we can print how many models we use and to have a look to see if all the models succeed. So we can try to run the cell and it will return us the result. So now the result is already in this maps 2099. So before we plot the result, you can also, as I mentioned every time, if you want to have a look of what's inside the variable, you can quick plot it, quick print it. You can see here. So for each one, it's a X array, data array, and now you can see our spatial resolution is reduced because we only select the grids in the Strait of Messina. And in general, in our case, because we have a 1+1 grid, so in our case, we only have 30 grids in that area in the Strait of Messina. So it's very close because for each grid, it will be 100 kilometers plus 100 kilometers. And here you have the same coordinates, longitude and latitude. Okay. And now the number is still the desk error. So it's still not the number of the wind speed. Okay. Until this step, we still get the desk error. That's the reason why to keep these kind of steps very quick, because it's a kind of lazy load. Okay. And also we can print the list of the name of the models. Here we are. So we get all these models. And finally, we can plot the maps as the same as we did for the observation data set. And we define this mean and max for the color scale, because we will plot all the results for all the models in one figure. And we need to make it consistent across different models, so it will be better for the visualization. And because we have 22 models, so I create a panel with 4 rows and 6 columns, so it will be 24. And the last 2 will be removed because we only have 22 models. And then, so this one is used for plot the color bar. It can be ignored. So here is the loop for plotting. So every time in the loop, we will create a subplot figure for that model. And then we select the data inside that model. And we give the title, use the model's name, and we made it increase. We made the setting for the latitude and longitude within this region for the plotting. And we use this mesh plot to plot the map. And it's important that only in this step, the real number from the store will be loaded into our work environment. Okay, so in this step, it will compute everything before and then return our target. Our target is the regional annual daily maximum wind speed for the Strait of Messina. And we add the coastline and the country borders. And here is for the format. We give the format of latitude, longitude, we set the title, we set the labels, and we add the color bars. And finally, we also can add a summary of the entire field and show the field. Okay. Let's try to run this cell, and it takes around 1 minute to 3 minutes. It depends on the connection. Sometimes if the connection is well, it will be quick for the calculation, but sometimes it might be slow, because only when you plug in here, it's actually calculating based on the actually loading the real data, not the lazy data, into our memory. Okay. So we can wait for the cell to run. Okay, so it's already 1 minute. Maybe this time we need to 2 or 3 minutes. Let's wait a bit. Okay, I think it's close to finish. Okay, now you can see from this figure, we get all the results from different models. You can see the name of the models and the wind speed in the Strait of Messina as we defined. But remember that this map is only for 1 year, so the annual maximum wind speed in 2099. Okay. And the color here, different color represent different numbers because we keep all the colors, all the maps with the same range of the wind speed. So in some maps, you can see, for example, this model. In this model, their wind speed is somehow lower than the others because the color is light. Okay, so it's around 4.5. Okay, and in this MPI model, you can see it's actually reach to the largest, to the 15 meter per second. So here I show you how to have a quick look of the special wind speed at a given year. You can try to multiply the year to different years after 2015 and before 2100. I will just multiply the year in this part, okay? You can either modify in this function, its default setting in this function, or you can modify when you are calling this function. So it's the same. You can modify here. It's better to modify here because if you modify here to 90 to 2098, it means that you give a default value to this function. But once you use 2099, it will change. It will use the actually passed value here, okay? So multiply the year here, and you will get the result for different years of the wind speed map. And we can also save the result to our local machine for the report. And next, as we did in the first notebook, we want to estimate the time series at the location of the Strait of Messina bridge. We want to see what is the future time series of the wind speed in this bridge, the location of the bridge. So we need to do the similar interpolate for different climate models. So we will define the location of the Messina bridge. And then, so this is the similar function to ensure the consistent latitude grid, latitude and longitude grid. And here is what we define for the interpolation or interpolate to the point, okay? So for every model, we run and we call this function in the loop, and it will make the interpolate for every model, and we get the model output for the Strait of Messina bridge for the future time series. Okay, and after we get the original time series, we can turn the daily point series into the annual maximum wind speed. We can define a function here for the annual maximum time series, and we select the time period. So it will be the same as what we did for the resampling of the error file. So it's the same resampling method, and we convert the series into Panda. We give it a name of the annual maximum surface wind speed for every model. And for every model, we return this Panda series. Okay. So by defining these functions, we can call in these functions in the loops very easily. So we call the functions here to extract the point time series, and it will give us the time series. So here, like this is what I mean. We need to use this load or compute. It will load the exactly data into our memory. So it takes time to compute. Because I would like to compute, and then if we compute once, we can store the result and reuse the result every time. So we don't need to take 1 hour for computing this time series every time. It will be very, very complex. So if you run this part, it will finally return to you. Oh, okay, let me continue. So after we load the data, we calculate the annual maximum, and then we put all the time series into a data frame. So in that data frame, we will have the rows represent the year from 2015 to 2099. So each row represents that year. And we will have different columns. Each column represents the time series from one model. So it will be a data frame containing all the model time series. And finally, we can also do a calculation of the multi-year ensemble mean. So we calculate a mean value for every time series per year. So we will get a time series of the mean value for 2015 to 2099 for model models. And we store in this data frame. Okay. We will not going to run this cell in this course because it will take 1 hour. And you don't need to run this cell because I already calculated. You can see the result, okay? But I also save it. So after my calculation, I save it into the local machine and download it. And now I already loaded into the Google drivers, so you can click here. So we also don't need to save because you already have it. And click the download. Okay, after we download it into our local computer, we can do the same. We upload it into the working file. Okay, so we put it here. Okay. Now we can find the pre-calculated result here. The document is here. We can directly read this calculated result. So we already directly load this dataset, the calculated dataset, the time series. So if you click the rounding cell here, you will get all the time series for every model in a data frame. Okay. For sure, the result will be the same as this one, because this is what we calculated and saved. So it will be the same. You can say from 2095 to 2099, the numbers should be exactly the same as here. So it's the same, okay? And then we can use the pre-calculate result to plot a quick look of the future time series of the Strait of Messina Bridge from all the models. In our case, 22 models and one multimodal example. So we use the data frame here. We make a copy for plotting, and we will get. So at the beginning, we exclude the MME for the loop because it will be easier. Because we loop the columns for the models by their names. And after we get all these parts, so we use all the models results to calculate the quantile of all the models. We first calculate the 25 quantile and also the 75 quantile. It's easy to use it by defining this axis minus and this axis equal to 1. So it will make into comparison within that year, between different models, and return you the quantile. So now we already have all the time series and the multi-year mean time series, and also the quantile series. We can define a plot, and we use a loop to plot every model, and we made it not that significant and give it a lower alpha. So it will be not that obvious in our plot because there are too many. These will be 22 lines. And then we fill between the 25 to 75 quantiles. It will represent the uncertainty range of the entire model ensemble. Okay. So the 25 and 75, it will means the range of 50% possibility of the model locating within this range. And finally, we plot the multimodal mean in a thick red line. So it will be very obvious in our plot because that's what we want to emphasize. We want to look what's the multi-year model mean tells us. Okay, and then finally is some definition of the labels and the titles. So it's the annual maximum daily surface wind speed at the Strait of Messina Bridge on the high emission scenarios from CMAP 6 from 2015 to 2099. Okay, and we can run this there. So this time it will be very quick because all of these results is already pre-calculated and loaded. Otherwise, if you calculate and plug it here, it will take 1 hour. So every time it will take 1 hour to create the figure. That's why the reason we only calculate once and then we save the result that we need. And it will be very convenient for our later analysis. For you, the same, you can save the pre-computed result and then use it as the plotting. So we click the rounding cell here, and it will produce a figure like this. What we can look is that in this figure, you can see different slightly gray lines. It represents the time series for every one model. So for example, here you can see here is the model we mentioned before. It significantly underestimates the wind speed. So it's around 2, no, even 2.5. So the wind speed is around 2.5. And there are some models is around 10 and 11. So not here is 3, sorry, here is 3. And here is 11. So you can see there is a very large spread for every model, from the lowest one to the highest one. But you can also find the majority of the model, they are concentrated near this range, like from 5 to 9, right? Maybe within this range, there are 19 models. So there are 19 models within this range. And only 3 models show very significant underestimate or overestimate. But in general, all the models, they are underestimate the wind speed. Because did you still remember? In our case, in the error file, even in the error file, not in the real observation. Because as I mentioned, the error file is a data set. It's a reanalyzed data set. It can underestimate the real observation. But in error file, the largest one is 70, more than 70 at 1973. Okay, so in this case, actually all the models, they are underestimate the annual maximum daily wind speed. Why? I will explain why in later section. Okay, and here you can see the gray range. The gray range is what we calculate. From here is the 25 quantile and the 75 quantile. So 25 is lower and 75 upper. So for example, how it calculates, in each year, we will have 22 values from 22 models. So we calculate the 25 quantile for these 22 numbers, and we get a number here. And we get another here, and we feel between the ranges of the 25% quantile and the 75% quantile. And for sure, lastly, the red blonde line is the mean value for all these 22 models. So it represents the mean value for all these 22 models. In general, we can use this multi-model mean time series to detect the changes of the climatology of the annual wind speed or the trend. But we cannot compare it directly with the observation, because you can see here all the models, they are exactly underestimated. So there are several reasons why the models they are not really replicate the observation behavior. I will explain in detail in the final note. Okay, so until now, we already learned how to load the climate data without downloading and regrade it to a common grid. And we can plot the maps for the wind speed. So here we plot the maps. We have the maps for the wind speed, and we also have the time series for the models. Okay. Finally, as I mentioned before, both the error type we analyze and the CMAP six, their outputs, they are great data sets and the model output, because the reanalyzed, they are data assimilation model output, and the GCM are climate model outputs. That means that some simplification or their grid representation, for example, here, the atmospheric and surface conditions like temperature, wind, is represented on a discrete grid. And within each grid cells, it's only have one data point for the time series, and it represents the area average value rather than a true point measurement as the real world station observation. Okay, because for example, for the error file, within each grid cell, it represents the average value within the 25 kilometers plus 25 kilometers grid. And within the climate models, it represents 100 kilometers plus 100 kilometers. So that will case very important consequence for extremes. For example, extremes are often smelled out because real world weather can produce very sharp local peaks. For example, very hot urban hotspot or very intense gust near the strait. But when the model and the reanalyze reports the value of that grid, it will give you an average of the entire cell, entire area. So in general, it will underestimate. So you can see from our result, it underestimates the extreme. And the closer the grid, and you can also notice from our result, and the stronger the smoothing, because the error file is relatively higher resolution, but still average at 25 kilometers. So it will have like 70 meter per second. Okay, so CMAPS is even much closer. It's, in our case, it's 100 kilometers. So it's even underestimate than the error file. Because we don't have an observation, because we don't compare our error file with the observation. But I think error file is still slightly underestimate the real world wind speed, maximum wind speed. So that will result. Grid data may underestimate the extremes. So whatever peak daily maximum temperature, in our case, we notice that the annual daily wind speed is underestimated. But in other case, for example, in the peak daily maximum temperature, the hourly gust, the flash flood, rain rates, all these variables can be lower, would be lower in the grid product than what a station will actually record at the most exposed points. So for example, here, if we have a station in Bologna, so the station will record everything, the temperature, the precipitation, and also the wind speed. When we compare it with the grid that come in the error factor, the climate models, which around the location of the station, actually both the error factor and the global climate models may underestimate these such extremes. So it's very important. And that's why the reason I introduced before in the introduction part. In general, before we do the impact study at the local scale, the error file and the GCM output is often need to be bias corrected or downscaled to the local scale to compare or to match with the real observation, the real point observation. But another important note is that this kind of underestimation or bias is not wrong, and it's very matters for impact study. Because the climate models at the beginning they are not designed to perfectly reproduce the local time series. Like they are not designed to reproduce every single point observation, but they are designed to capture the large scale climate statistics and what will be the forced changes. For example, we can analyze the trends, the patterns, the seasonality, response to different emission scenarios. For example, here we can calculate the trend of the future wind speed time series or their seasonality or their patterns on the different emission scenarios. Okay, so this is what we will need by using the climate models and their indications for the future scenarios. It's also very important because for engineering, infrastructure safety and risk assessment, we will not directly take the road resale maximum as the worst case, but it can be served as a lower bound. Okay. What does it mean? Like if the climate models they project a very high risk of kind of extreme event, we cannot ignore such possibility. Because once if every models they agree, so it will have a high confidence of such kind of scenarios or of such kind of extremes. We can take this kind of extremes as our lower boundary to make a more robust future design of our infrastructure to mitigate the possible climate change. So that's why the climate models should be used, but not directly compare the numbers within the past numbers. So finally, I'd like to give you some notes about when we talk about the future extremes. Whatever, for example, heat stress or the wind speed or the heavy precipitation, by using the error file or climate models, this kind of grid dataset, we should always remember that the grid climate data, they tend to smooth the subgrid variability. And as the result, the true physics experience, or the true experience that could happen in our real world or recorded in the past station data can be more extensive than what this grid product records. But still, these datasets are still the fundamental tools for us because the grid station data are not always available and they cannot cover every area in the world. For example, in some continents, the stations are dense, but in some other continents, the stations are not that will cover. So the ERVI and the global climate models, due to their global coverage and due to their simulation from past to the future, we can use them as a tool to analyze what is the possible future extreme looks like by looking into the statistic patterns, for example, trends, seasonality, rather than the numbers. Okay? So this is the part about the climate models. And today it will be the last lecture of my section. In summary, my section contains two parts. The first part is an introduction about the downloading and using data from the Copernic data store. And then we do some statistic analysis about the annual maximum wind speed. And the second one is about accessing the climate model dataset and doing some analysis about the wind speed map and the future time series. Also, for sure, you can do some similar analysis as we did for the return period in the previous notebook by using the output from the climate models to estimate the return period. Okay? The theory is the same, only the input data is different. And if you have any question about in using these two notebooks, or if there are any unclear parts during my lecture, I'm always willing to answer your question by using the email. So you can always write the email to ask me, and or if you have any problem in using my code to building your analyze, I'm always willing to help. And thank you very much, and see you next time.